Alright, welcome guys. I am Harijs from Passionate People. I've been here almost for 3 years. I specialize mainly in front-end technology, so that's all things JavaScript and TypeScript. Been working a lot with Angular, Vue and some React. So a lot of the time has been spent in TypeScript code bases. Sometimes I do also a bit of Java and Python, and I like Rust for fun. And today I'm here to present a workshop on Advanced TypeScript. Normally in a real life scenario there would be more interaction with attendees and more questions and answers as we go. However, we live in special times, so this session is pre-recorded for JSworld Conference 2021. So it will be mainly in a presentational format, so I'll be going through various slides and trying to explain more advanced TypeScript concepts. I hope I can explain it from most angles that are relevant, and that it will facilitate your understanding of TypeScript quite a lot, and you'll be able to apply this knowledge in your daily work. This workshop does require some prerequisite knowledge. You should be at least familiar with basic types, obviously numbers, strings, arrays, and that sort of things. You should know what any is. Perhaps you haven't seen unknown or never in practice that much, but we'll go over that a tiny bit as well. But that's not relevant for that much for this workshop. However, if you feel like you need to refresh a bit of your TypeScript basics, official documentation handbook is a very good place to start, and then you can try continuing with this workshop, or you can just watch it now and go back to the handbook. Some things will dawn upon you, and then rewatch this again, and you will gain even more deeper level of insight. That being said, it would be beneficial if you already are familiar with things as tuples, enums, type unions, and intersections, because those are the things that obviously we'll be building upon. You should at least have encountered interfaces and type aliases, although the first part I want to look at them both and specify the differences. Would be great if you knew what literal types is, although it's not that difficult concept, and we will definitely look at that. And obviously would be great if you knew what classes are in ES6 and TypeScript. Sorry, I meant ES5. Alright, so plan for today is to start briefly just looking at the interfaces and type aliases, then dive into conditional types, some type manipulation, go through various utility types TypeScript provides us out of the box, then look into generics, and finally in decorators. So more or less these topics are arranged with ascending difficulty, although maybe the last two are disputable, the order of those. If you're completely new to these topics, perhaps it's a good idea to pause between the sections and maybe take a break to let the concepts to sink in, because we'll be looking a lot of examples, and it might be a bit overwhelming to consume all that content at once, especially if it's the first time encountering that. Alright, that being said, let's start. So the first topic I want to discuss is interface versus type aliases. Just briefly look into those. So what are types? Type aliases in a nutshell is a TypeScript way of giving a new name to some already existing type. The most useful cases are for naming a union or intersection type, giving a new name to a tuple type, or naming a type that was derived using utility types. So some of those examples are, for example, giving a name to this number and string intersection. So giving a new type name for a thing that can be either a number or a string, or giving a type name RGBA to a tuple type consisting of 4 numbers in an array. Or, for example, if you have an interface with a blog post where you have 4 properties, but you want to derive a new type which is just a blog post preview, which only includes the title and intro properties, by using the pick utility, which we will later look into. You can give that a new name without having to specify what it contains. Simply you can derive it from existing interface and using utility type. So these in principle are the most useful applications of type aliases. But when it comes to interfaces, yeah, both are very similar in many ways. All interface features are available in types. So you can have nested types, you can have recursive types when you refer inside the type to itself. So you can have like a nested structure that goes infinitely deep. Only thing you cannot have in types which you have in interfaces is opening that type and adding new fields when it's already existing. I will show you an example in just a second. So type cannot be changed after it has been created, but both of them can be extended. So extension is done in the case of interfaces on the left side through extends keyword. So we have this very simple example of vehicle and airplane. So in this case, airplane extends the vehicle and adds a new property. In the result, airplane will have 2 properties, both name and airborne. In the case of types, you can achieve the same thing by giving a new type by combining vehicle and this literal type with airborne property. So in essence, after the fact, both of these will behave and work exactly the same. However, when it comes to adding fields to already existing interface or type, only interface case is possible. So on the left side, if you already have an interface vehicle, you can refer to it once again and keep adding new properties. And at the end, the vehicle interface in this case will have both of those. So interface can be opened and new properties to it added. However, in the case of vehicle, in the case of type, that is not possible. TypeScript will complain you that it's a duplicate identifier that already exists, so you no longer can change existing type. Right, that concludes basically the difference between interfaces and types. Next I want to look into conditional types. So this is one of the actually sort of more advanced features which you probably have encountered if you have read some TypeScript code and perhaps even used. And in a nutshell, it helps to describe relationship between types of inputs and its outputs. Syntactically, it's the same principle as in JavaScript expressions. So with ternary operators. So when you have expression and question mark, if that expression resolves to true, then the first branch is taken. If not, then the second branch is taken. It is most useful in combination with generics, because here in this example, we are creating conditional type, in this case a result type, asking does airplane extend vehicle, and if it does, then the type is string. If it doesn't, it's a number. Clearly here at compile time, the answer is already no, so this is very contrived, very simple, unrealistic example. But clearly the resulting type is string because it is this is true. But in practice, you encounter these conditional types in the context of generics, where it makes most sense because you don't know at the compile time which type it will be, and only when actual type is given to the method, only then the conditional type can be decided. So here in this case we're using a generic type t, which we will look into later. And basically the extend syntax means asking, in this case, sorry, this means this is a generic type guard or boundary. It says that generic type t has to extend Boolean, so it has to be of Boolean type. And here we have the conditional type, where it asks, does the type extend true, literal value true? Basically means, can it be assigned to value true, or is that Boolean true? And if it's true, then the return value of this function will be a string, otherwise it will be a number. So this, for example, in this case, getID is a function where we, let's say, querying some system, and we're just providing whether it's a legacy system. If it's a legacy system, then that system has string IDs. If it's not a legacy system, it's number IDs. So by that already at the TypeScript level, during compile time, we know that if we provide value true as an argument to this function, the resulting type will be string, so TypeScript is able to detect that. If it's false, it will clearly see that it's a number. However, if we don't know even in compile time which it will be, whether it will be true or false, so we pass in a random value, TypeScript is at least able to deduct that it will be a union of both truthy and falsy conditional type values. So in this case, it's union of string and number. Conditional types come really useful in contexts of filtering unions, for example. So in this case, let's imagine we have a couple of example types. So we have a cat and dog type. They have either each own property, so cats meow, dogs bark. And then we have a bit more expanded types, so we have cheetah and wolf. So both wolf and dog bark, but wolf also howls, and cheetah and cat both meow, but cheetah is also fast. So here we can create ask a conditional type question. Does the type A extend literal type barks true? It basically means, can type A be assigned to this one? So out of these four, obviously only dog and wolf could be assigned. So here we're creating a new type with generic type argument A, where we are asking if that generic type extends this literal type, so barks true, then we can return that very type A. Otherwise, return type never, which in practical terms means it will not return, or it will skip returning anything from this type. So in practice, how it looks like. So if we would have a type of all the animals in a union, so we have a union of different animal types. If we now pass that type union to our created type function, so to say, which filters only on the types which bark, in result we will get a new union type only with dog and wolf, because those are the ones which bark. Conditional types can also be used in combination with infer keyword. An infer keyword lets you to look inside another type's generic argument. So in this case, in an arrays argument. So we can create a type with generic argument t, where we ask whether that generic type extends array, or basically is it a case, is it an instance of array? And if it is, we infer what type of array it is, so what kind of elements that array has. Then we return the type. Otherwise, we return that very type that was passed in, type t. So in practice, it means if we get a simple type, we return the type. If we get an array of types, then we return the type of which it is an array of. So, for example, if we have a type of either a single dog or an array of dogs, then by passing that type union to our newly created flatten type, it will return only a single instance of a dog, of a type that has bark set to true. So that's something you can achieve using conditional types in combination with infer keyword. Another small thing to remember is that conditional types are distributive. It means that they are applied to every member separately if the passed in type is a union. So what does it mean? It means that if, for example, let's create a new type first, the opposite of we did before, so opposite to flatten. In this case, we make an array of whatever there is. So whatever we type we get, we create an array of it. So because any type can be any type extends any, because it can be assigned to any type. Therefore, the truthy branch will always be true. We'll always get an array of the types we pass in. So, for example, if we pass in a string, we will get an array of strings. But where does the distributive property come in is when we pass in a union of either string, number, or a symbol. One might think that we would get an array with this union as a type. That is not true. What we actually get multiple individual array types created and then joined in as a union. So we get first either a string, either an array of strings, either an array of numbers, or either an array of symbols. Right, that is about conditional types. So you can take a pause or rewatch the previous section if it was hard to wrap your head around it right away. And next we'll continue with type manipulation. So first thing I want to talk about is the type of operator. We know type of operator from JavaScript already because it can be used as an expression. So if you have a variable, you can type of and then the variable name, and JavaScript will return what is it type of. Is it an object? Is it a number? Is it a string? Is it undefined, for example? However, in TypeScript you can also use the very same operator in type context, which means syntactically in a place where type should go. So let's say we have a variable called nickname with value Joe, and here we are assigning type n and then the equal sign. So everything that follows after equal sign and ends with semicolon is a type context, because that's where we define a new type. So we could write anything there, like we could create a new new interface there, new type using some utility type. But here we are writing type of space and then referring to the variable name. So that assigns to this type n whatever type the nickname has. And in this case, nickname has a literal type because it's just a string value, Joe, and it's a constant. So therefore TypeScript knows that it's not only generally a string, but it's specifically string Joe, and since it's a constant, it will never change. That's why it's string literal. And therefore, since we wanted to assign to n the type of nickname, the type of n is string Joe. Similarly, let's say we have this plain object representing car with 3 properties. If we want to create a type, let's say car type, and we assign it to the type of whatever this variable car is, and then this car type assumes the shape of 3 properties where brand and make are strings and top speed is a number, because TypeScript infers that from this object. So for example, that type of operator can be used also on functions, because functions also do have a signature type. So in this case, this is a function that takes no arguments but returns a boolean. And if we would use a utility type of getting your return type from a function type, then we see that type of random's return type is boolean. Another useful operator in TypeScript is keyoff. I'm sure you have seen it probably, but sometimes using it together with other operators or finding the right context to use it can be tricky. But in principle, it works very simple. Keyoff operator takes keys which exist on a type or an interface and creates a literal union of all those keys. So for example, if we have another object of car, in this case we have a type and a wait key, and here we assign a new car props type. So first of all, we get the type, whatever type the car has, and then we get key of the keys of that type, and in this case those keys are type and wait. For example, if you would apply this operator on the window type, which is part of TypeScript library, then you would get a literal union of more than 220 string literal types, because those all keys exist on the window object. There's something called indexed access types. So I think they're pretty intuitive and obvious, because it follows basic object accessor syntax. So I imagine if we have this interface of building where you have area, floors, address, and whether it has underground garage as properties, then if we want to get the type which one of these properties possess, for example, in this case we want to get the type whichever building area has, we can do it so by indexed access, and therefore our building area type will clearly be a number. By the way, this interface building is used throughout multiple examples. So this particular one where area is a number, floors is a number, the address is a string, and whether it has an underground garage is a boolean, occurs multiple times in the following slides. So if you see building referenced without the actual interface definition, that this is what it's meant. So that might aid your understanding as you continue watching this. So with the indexed access, one simple way is of course typing out the property you want to access, and then that resulting property will be assigned. However, you can also combine it with the keyoff operator. In that case, the resulting type will be a union of all the different values that type has. So if we pass in the union of all the keys that building has, then this resulting type is union of all the types of values building has. So in this case, building has numbers, strings, and booleans, and by iterating through all the types through indexed access, we get all the property types this type has. In case of arrays, you can use number, because array items are accessed through numbered indexes. So for example, if you have just a literal array with some literal objects which are of similar shape, let's say we have name and count. So if we want to get a type of arrays items, we can get it by writing the array name, so in this case items, accessing its any member by using number keyword, and then getting a type of it. The next type manipulation concept I want to tell about is the map types, which allows to keep things dry, so don't repeat yourself, and base the new types on existing types already. So it basically allows you to iterate through the keys by using the in and key of operator. So we already know the key of operator, which returns a string union of all the object's keys. And in keyword can be used in this context, where you go through every key in the key of and perform further type manipulation. So for example, here we are creating a new type, a new object, where every key corresponds to the building key, but in this case value is a function. So in this case it's a building property formatter, let's call it that way, which is a function which takes in the same type and returns the same type. So area now is a function that takes in the number as an argument and returns a number. Address takes in a string, returns a string, and underground garage takes boolean, returns a boolean. So basically, with this syntax, you are able to computationally create a new type without having to write it out by hand. So saving some time, and of course in the generics section and also utility type section, you will see how it can make things generic and reusable if you instead of using here hard-coded type building, but if you would use a generic type. So this sort of same principle could be applied to any interface or type. With mapping types, you can use modifiers. For example, if you have a interface where all properties are read-only, or maybe even just some, let's say locked user, with map types, as you iterate through every key, you can, for example, remove the read-only modifier. And the syntax is very intuitive. It's just minus read-only. So here we iterate through every key of the locked user, and the key's type is the very same. So if it was a number, it still is a number. If it was a string, it still is a string. Only thing is changing that we're removing the read-only. So the resulting mutable user type has the same properties with the same types. ID is still a number, username is still a string, but the read-only access modifier is missing. It has been removed as we mapped over the types. Same thing can be done with removing optional. So if you have a type where all properties, or just some, for example, are optional, by mapping over the type and using the syntax minus question mark, you are essentially removing that optionality. So you make that property required. So in this case, from all properties being optional, you get something which has all properties mandatory. In combination with template literals. We'll just look into that just after a moment. But using as then a new type name syntax, you can even rename existing property keys to new names by using some computational logic you decide. For example, if you were to create a, let's say, prototype building, and you want to name prepend and append to every key double underscore both ends, that can be done using this as syntax and template literals. So by using mapping modifiers, you can achieve that very easily and computationally without having to redefine the whole type. So it can be used even with more utilities. For example, you can devise a new property name that is capitalized. So let's say we have a type, the very same type building, and we want to create a new type which consists of getters, where every key is every key's value is now a function that returns something and returns appropriate type. But in this case, we are deriving a new name for every property. So instead of area with lowercase, we get area in camel case. So that is all possible with map types and mapping modifiers with as a new type syntax. And this brings us to template literal types, which is a very nice and cool addition, starting from TypeScript 4.1. So it's just the same syntax as we have in ECMAScript 6. So with the backticks and then the $sign with curly braces, or we put it in a variable. We have template strings in expression context, but we can use it now also in type context. So for example, if we have a type which is a string literal red, we can devise a new type with a string with a template literal type, let's say bright red, which puts in front bright and space, and then whichever value that other type is. Now, where the great power and beauty of this feature comes in, if we have a type of consisting of let's say a string literal union, so we have, let's say, multiple colors or different sorts. If we want to create a new type based on the same union, so let's say all these 7 colors, and just prepend dark in front of them, we can do so with template literal syntax, and in the outcome we devise a new type consisting of all the string literal types we had in the beginning of all the union, just with dark prepended in front of it. So also a great new feature. What is even greater about it is that it creates unions with every possible combination. So if you're using multiple unions inside a template literal type, TypeScript generates all possible combinations. So let's say we have 5 different locales and 4 different sections. So if you want to create a locale string ID type, we just need to specify this template literal type, and TypeScript will generate all the possible combinations that we can obtain. So in this case we have 5 by 4, and that is 20 resulting union types. And yeah, it can be used with the utility types or string manipulation utilities that come with it. So if you want to modify the string literal in a way in a template string, so you can cast it to all in uppercase, all to lowercase, capitalize only the first letter, or uncapitalize the first letter. So that is all possible with the template literal types. All right. That concludes the type manipulation part. Again, you might take a pause, let it sink in what we talked about, and proceed when you're ready. Next, I want to go over all the built-in utility types which we have in TypeScript. And one way to think about them is functions. For those are basically like functions for types. You pass in one type into a function or a utility type, and you get out another type. So it takes one type as an input, returns another one, or maybe sometimes more. Sorry, it might take more than one as input, but always returns a new one new type as an output. So the very same interface we are already familiar with. So just for multiple examples, so we have a building which has an area which is a number, floors is a number, the address is a string, and whether it has an underground garage is a boolean. So there's a utility type partial which sets all the properties as optional. So opposite to what we looked into map types, so we can get manually by creating a new type which goes all over every key and sets everything to required. You can have a type which makes all the properties optional, so by using partial. However, small feature to remember that it only works on the root level properties. So let's say if you have root level only name and owner. However, owner is of object type which also has a name property. So only the root level properties become optional. So if you are going to provide owner in this case, the name property then would be mandatory. It wouldn't be optional. We have read-only utility type, so it sets all the properties as read-only, even though they were mutable first. Now they are read-only, so which obviously means that if you would try to assign a new value to it in the code, TypeScript will complain. We have required utility, so basically it does the same thing what we looked into map types. So it removes the optionality. So if we have interface exercise where type is a string which must be present but intensity is optional, we can create a new type where all properties are necessary, are mandatory or required. So we get that out of the box by using required utility type. Now, this is a first utility type we're looking into, which requires two inputs. So it requires us string union type for the keys. So what kind of keys the new record, the resulting object or interface type will have. And a second argument, it needs a type. Is the type of the values that every property will have. So let's say we have now we're gonna have multiple buildings. So we're gonna have main building, the guardhouse, guest house, and service house or service building. And we want to create a property type, property interface, which is a record of all the buildings, and every key's value should be a building. So now we get an object with all these keys specified in this union type, which you can also pass in literally. But here we're just giving it a name for easier sort of understanding. But this lets you computationally create new types without typing them all out explicitly. So instead of typing and using 6 lines, you can achieve the same output with 2 lines. Another, of course, feature is just like with typical expression code, you can combine utilities, and instead of passing name types as arguments, you can pass in result of another utility type. You combine utilities as far as you want. For example, here we are creating a read-only property where all the keys of all the buildings are read-only. However, the values are partial in this case, so that is also completely achievable. Here, by the way, it's showing 3 dots just because the tooltip window was a bit too narrow. That's why I couldn't. I don't know why it couldn't show it. All right. Our next utility type is a pick. So it takes a type and just selects from it only the keys which correspond to the interface. Union type passed in a second argument. So in this case, if we want to pick only area and floors from building type and create another type, this is a way to go. Opposite to that would be omit utility type. So basically it takes in type and omits or ignores the property keys which you pass in as a second argument. So in this case, if we want to get rid of area and floors and just keep address and underground garage, then we can use omit utility type in this kind of way. Exclude utility type lets you remove certain members from a type union. So let's say if you have a type which is either numbers or strings, so either a single number or an array of numbers, same with strings. If we want to exclude from that union everything that is either a number or an array of number, we can use exclude utility, and as a result then we would get only the union types which are not assignable to this union members. There is no error if you pass in too many types, so it only skips the ones which it encounters here. So you can try to exclude multiple or more which may or may not be present in this union. Extract works similar but in opposite way. In this case it only keeps the union members which are assignable to one of these. So in this case, if we have the same numbers or strings, we only want to keep only array types, so either a string, number, or boolean. Even though our this type doesn't have booleans, it still works because it only looks which could be present there and which could be kept or extracted. So in this case, from this one, it gets rid of simple number and simple string and keeps the array types. Non-nullable utility lets you remove null or undefined members from a union type. So if you have a type which is maybe buildings, so it either be a building itself or an array of buildings, or a null or undefined, if we apply a non-nullable utility type to create an, in this case definitely buildings type, then it will remove all null and undefined union members. Parameters utility type can be used to get a tuple representing a function arguments types. So imagine we have a simple function called repeat string. So first argument is a string, second is a number, basically how many times we need to repeat that string. As a result, it also returns a string, so basically the type of it is a function which takes in a string and a number and returns a string. If we apply parameters utility on the type of this repeat string, so then we can get out the tuple which corresponds to the arguments of that function. So for example, here if we want to get the type, the arguments, we use parameters utility function. A common mistake is to pass in the function name as a parameter to the utility type. However, it should be type of, because in this case it is a type that this utility type accepts and not the value itself. So that's why we need a type of in front of the function itself. Similar with the constructor parameters. So let's say if you have a class, let's say an animal, which takes 3 constructor parameters, we can extract those in a new type by using constructor parameters utility. So here again, similar idea. Have to use type of the class, not the class itself, and then we get assigned the tuple to this newly made type, which is a tuple of 2 strings and number. And if we were to use them later in code, for example, then you would call a tuple or an array in this type, pass in correct type, arguments, correct order, and then, for example, instantiate a class with that tuple. So for some examples, with available constructor definitions from TypeScript library, for example, you can get error constructor parameters or regular expression constructor parameters, or even set constructor parameters. Return type is when you want to get the type whatever function returns. So if you have already mentioned repeat string function, which took in string and number and returned a new string, we can use, for example, if we want to have a something dynamic in our type system that automatically assigns to a type whatever some function returns. So you can use return type. Here it correctly assumes that it's a string. You can also use that on built-in functions. For example, use the type of the setTimeout function, and the return type, if used in Node.js context, is a Node.js timeout, for example. Instance type gets you the instance type of a class. So in this case, instance type of animal is an animal. Yeah, it looks kind of useless and simple in this sort of context, because we are getting a type of class we already know of at the time we write it out. However, it comes actually useful in real scenarios when used with generics. Also, there's utility type to extract this parameter type. So if a function uses this and it's passed in as a parameter, with this utility type you can extract it. For example, this lets you to type it to a number. However, if a function doesn't have this parameter in its arguments, then this utility types return unknown. So just like it is in the case of setTimeout. So with all what we've looked at, it's possible, of course, to build our own custom utilities, because if you look into the code of how these utility types are created, they actually are written in pure TypeScript, just using the existing constructs we looked at. So partial is basically generic type, which accepts generic type T, goes all over all of its keys, adds the optionality question mark, just like we looked into in the map types with the p in key of syntax. So similar with with the pick and record. So if you want to dive into that, you can see how all those utility types are constructed just using TypeScript means and syntax. So that lets us, for example, create our own utility types if we choose to. For example, taking advantage of the index types, what we did, right? Getting all the types of the values of type of an interface. We can, let's say, create a utility type of values where we get a generic, take a generic type and return the values of all the keys of that type. So, for example, if we would create our type utility this way and pass in the building interface to it, then we would get all the values that the properties of that building can have. So you remember those were strings, numbers, or booleans. If you want to dive more into different useful custom utility types, this is one interesting repo I found. Utility types, so you can Google it and find it. Has a lot of interesting examples. Actually, some of them are overlaying already what TypeScript provides, but I assume that is because this library is a bit older and TypeScript has been introducing its utilities over time. Alright, that concludes the utility types. Again, take a pause to let it sink in what we gone over and discussed. And next, let's start with generics. So the next big topic I want to talk about is generics, which in a nutshell basically you can put it as types, as variables. So it could be any type. There is such a thing as hello world of generics, so the basics of it. You can even find that in TypeScript handbook docs. So let's say we have an identity function, which is a primitive function. It takes an item and returns that very item. So whatever it takes in, it returns. Without specifying types, TypeScript assumes that item could be of any type, and therefore return type is also any type. So it can take anything in and could also return anything. That's perfectly what the identity does. Takes in a thing and returns the very same thing. However, when we would pass in a string to such function, TypeScript would assume that the return type from that is of any type. Even though we clearly know it's a string, it loses any information and assumes it can be anything. So either it's a string or a number, still the resulting type is any. So at type level we completely lose any information. Although we would like this function to work with any type, we would still like to keep a track what it is we get out of it, because what we put in is the very same thing we get out. And that's where generics comes in, because you can tell TypeScript to use a generic type. So basically a type variable can assume any type when used, and this is the syntax. So if your function is generic, you put these angular brackets in front of it after the definition starts. It's a convention to use capital letter T, but it can be any string, anything that starts with a string. It can also be a number afterwards. Typical convention is to use capital numbers for generic type names. But now, at least we know that we can specify with types that the very item we get in is of type T, so any type, and the return type is also T. So what we get in is the same thing we get out, also type-wise. So if we pass in a string foo, the resulting type is also string foo. Same thing with a number. Now, let's say we have a method that wants to update a metadata property on our item. And we also want it to be a generic function. We don't want to redefine for every type. We want to work with any type in our code base. All we want to do is take any type we might throw at it and set the metadata property to latest timestamp. However, TypeScript would complain us that the metadata property does not exist on this generic type t, and that's where type constraints come in. Even though we use generic types, which could be any type, we can put constraints on that. We can limit to what types those could be, and it's done again with extend syntax. And extend basically in simple language translates to, can the type t be assigned to this type? And in this case we have a type has metadata, basically has a property metadata, which is a string. So if that type has this property metadata, then we can use that function with it. So it can be any type as long as it has metadata property, and then we can modify it, and then the function will work. Generic constraints also work with using one generic type to constrain another generic type. So let's say we have a trivial method get property. So ignore this part for now for the types. Just the functional part. So get property takes in an object and a key, and it returns that key from that object. So relatively trivial function. If we wanted to work with types and be precise that way, we can define those constraints very easily. So it is a function that takes two generic type arguments, t and k in this case. So one for the type, one for the key. And here it is. So the object is of type t and key of type k. The type t can be anything, but the key that's passed in must be assignable to the key of the type. So let's say if we pass an object of keys a, b, c, d, the key of type will be a union of all those letters, so a, b, c, and d, union of strings. I'm sorry, intersection of strings, and the type key therefore must be assignable to that intersection. Therefore, this makes sure that whatever we pass in as an object, the key must exist on that object. So for example, if we would use that with these values, so we have a property object with keys a, b, c, d. If we would pass in here and try to access property a, it will work. But if we would try to access a property which does not exist as a key on this object, TypeScript will detect it and rightly so complain that type y is not assignable to this type intersection. Generic type constraints also can be used with classes. So if you want to limit some argument to a class, it needs to be sort of newable. So it needs to have a new method. So if you want to constrain only to accept classes, this is the type signature of classes. So let's say if you have a factory and you want to initialize any class, but you still want to type it precisely. So this is a way to do it, and that does force the class to be instantiable, so newable. For example, if you would use a class that has a private constructor, in practical terms meaning it cannot be instantiated, the TypeScript will complain. Typical generic type names we encounter, we saw it as T often, right, for the type, key for K, E for element, and for number often. It's very typical to keep using more letters, S, T, U, V, etc. for if there are more and more generic types. Also T0, T1, sometimes V for value. So typically generic type names are kept to one capital letter. However, there are also opinions in the community that we should give more descriptive names to facilitate understanding of the type system and in the code. Now, in its own, generic type doesn't seem that difficult, and they aren't. However, they can be also applied in a recursive fashion, in a recursive way, utilizing various type manipulation features to achieve pretty awesome results, but the outcome of it can be quite mind-blowing. And for this I want to show you an example and go to my VS Code. So here we want to show you to build a hypothetical class, let's say SQL query builder, which will build a query to pick out some fields. Let's say we will be working with these two interfaces, one with building, one with car, with these quite simple properties. And basically the outcome I would want to use is, say I want to start a new query builder. I would use maybe, first I'll start with car. If I want to make a query to database that, first wants to select the brand, I want to select the year, and then run the query, and have type information stay with it, so type information be preserved and built along the way, and be available to what I'm using. So here I'll leave this commented out so to see what we are building for. So let's call this one let's call it SQL query, and it will have two generic type variables. So first one will be the model we're using, so in this case what we are selecting, and the other one will be result, because we will need to keep keep track of what we have selected, what we have built up so far. We will definitely have a method to run, but we'll get to that. But we will have a select field method, which will be a function, and in this case I wanted to I want to skip the implementation part because I just want to focus on types. That's why I write null exclamation mark, which in TypeScript terms is basically ignore the implementation. Do not check type information of that. So first of all, we need to be able to select a field from the model we are using. So for example, can call it argument f, which we type field, and one way to limit that is to say that here we'll be using sorry, why is it, should be here, field extends key of model. So whatever model we're using, we want to limit the field to the key of model. So we don't want to be able to select properties which don't exist on the type. So that will already give us so let's call new query, be SQL query, and in this case we will we'll remove the result for now. So we'll want, as model, we want to use car and select, oh yeah, it's new SQL query. So we want to select field, and TypeScript already knows that the type car has these 5 properties, and if the field must extend one of those keys, then it is limited to only these values here. So if I would enter something else, TypeScript will complain, hey, you cannot assign this string to expected type. Similarly, if I was working not with car but with the building model, it would expect me to provide keys for the building. All right, so far so good. Now we also want to return the same query type because we want to be able to chain these select field calls. So we will return the same query build SQL model in this case with the same model, and that will, so if you want to have select address in this case, or area, so you can keep building and selecting more and more more fields. All right, but this so far lets us select the same item multiple times, even though it functionally would not make sense. You want to select a field only once and that's it. So how can we limit that? Well, we can limit that by using the exclude utility. However, we need to keep track what we already have selected. So that's where the second generic type comes in. So we'll call it the result. And here we will also have result. We will return it. And here we'll extend not the key of model, but we will extend the result of excluding a key of result from key of model. So here we need to, as here in this case, since when we initiate the new query, the result is of empty type, so therefore the second argument needs to be just an empty type object. So we got that going here so far, at least here. So the fields, the assignable fields, will exclude the ones present in the result. But so far, result is constant and unchanging. So we started with being an empty type, and it gets passed into the next return of the select field method to the same type. Now what we could and should do in this case, extend the result with adding what we selected, and that is done through in operator. So whatever we select, so that will be let's call it the key, that should be in assignable to the field type. So the key should be assignable to the field, and the type will be of the model key. And now we can see that area is no longer assignable to type floors, addresses, and an underground garage, because area already has been selected, and the next time this very same type or instance of the class is returned, the result has expanded and it now already includes area as a key. So therefore you cannot add it twice. And that way we can start to build up our query. So we can also select underground garage. So and for the final method, let's add the run method. It will simply be a method that returns a promise of the result, because it will query the database hypothetically. Also we're skipping the implementation. Oh, yeah, exclamation mark. So now if we run it, we'll return as promise, and TypeScript already knows that this variable q is a promise, so therefore you can use then on it. You can get the result, and the result will have these properties which we selected. So if we would now remove the floor, TypeScript will detect it only has area and underground garage. So this kind of things you can achieve with generic types when they are applied recursively. So just to illustrate a little bit more of it, if we were to use car type instead of selecting building type keys, so if we would car, this would immediately be wrong. TypeScript would complain about that, and the result would not have these properties, and only valid ones from this model are usable. So for example, you could use turbocharged and doors, and if used correctly, TypeScript will be able to know that the result will have only those properties which were selected. So that's about generic types. Again, if you need to take a pause before continuing further, and then next we will proceed with decorators. Okay, that leads us to the last section about the decorators. So decorators basically are annotation and metaprogramming syntax for decorating things like classes, methods, accessors, properties, or parameters, that is in current TypeScript specification. And all a decorator is basically a function. It has a syntax where you write @ and then expression, so whatever follows must be or return a function that can be executed at runtime. So the most basic decorator is this, just a function. Let's say a decorator name, accepting some arguments, and logs out whatever it got in. And if you would apply it to empty class, at the moment you execute this code, the decorator function is run as well. And in the case of class decoration, it runs as with the same class as in first argument and only argument in this case. In reality, mostly we see decorator factories, because that allows to pass in and specify some sort of configuration. So if you're coming from Angular background, you will have seen this a lot, because through this decorator factories, Angular embeds a lot of its functionality. So like assigning a template URLs to a component, etc. So, for example, here you would have a factory which accepts three arguments, and then that factory must return a function which will be the actual decorator. So if you would run this code, you would see that the factory was executed first with the arguments you passed in, and then the decorator ran with, in this case, with the class as the first argument. So there's nothing special about that. At the end of the day, it just has to be an expression that must return a decorator function at the end. So it can be a function that returns a function that returns a function. So a very functional programming sort of paradigm. But that is rarely useful in this context. So we typically see just a function accepting one object or one set of arguments. Decorators can be composed, so you can apply multiple ones. So let's say we have a decorator A, B, and C, and we all apply them in the same order, A, B, and C. However, when they're executed bottom to top. So the last one to apply is executed first. So that does something to the decorated object, the next one, and then the one you added first on top. That same applies with factories. Factories actually are executed from top to bottom, so whichever you apply first runs first, but the very decorators themselves go from bottom to top. So that's a small detail to remember. Now, decorators can be applied to 5 different targets in current TypeScript specification. Here I've created just a super basic decorator factory. So it takes in one argument string and just console logs what it is being applied to, and returns the decorator itself, which is basically empty function. And here in the decorator factory argument, I've just specified to what I am applying it. So we would see it logged out. So it can be applied to a class, it can be applied to a property, can be applied to a method, to a accessor, and it can also be applied to a method or a constructor parameter. And when we see it logged out in console, we can see that it runs from the last encounter to top. So starting from property, just because it was defined here last, not because properties are decorated last, but it was here decorated last in the code. But the class, even though it was defined first, is decorated last, but the rest goes from bottom to top. This is the tricky part to keep or to get your head around, which took me a while to sort of demystify this whole concept of decorators, is that they can be applied to 5 different parts. However, they are ran with different arguments, or at least somewhat different. So when you decorate a class, the decorator is ran only with one argument, and that is the constructor. And if it returns anything, then what it returns replaces the class definition during runtime with a new class or newly returned function. Method and accessor decorators accept 3 arguments. We'll go to those in depth just in a moment. If those decorators return anything, they replace the property descriptor. I will explain about that as well. And property and parameter decorator returns are ignored. And property decorators are called only with the construction function or the name of the property, and parameter, that is a method parameter or constructor parameter, decorators are called with the target or the class, the name of the property, and whichever index position that property had in the method or the constructor. But yeah, the returns are completely ignored. Okay, so let's look at the class decorators first. It's called with one argument, the class that is being decorated, and if it returns anything, it replaces class definition with whatever you returned. So here we have an example of a class decorator. It takes in, we have a factory in this case. We take some value and we return from it a new, well, we return, first of all, we return a decorator, and then we return a new inline class which extends the class we're decorating, and we adding another property to it with the value. So such a bit contrived example. So in this case, for example, we are creating a dog class which has a name and a number of legs, and we're decorating it with this class decorator with value foobar. And when we run it, we see that it has replaced the dog class with actually the extended class and has added the extra property. We extended it with the decorator. Method decorators are called with 3 arguments. So first is the class or the constructor function. Second is the name of the method being decorated. Third is property descriptor, and if the decorator returns anything, it replaces that property descriptor. What is property descriptor? It is something every JavaScript object has. You can access it using object.getOwnPropertyDescriptor syntax. So by passing the object as a first argument and then the property name as second, and returns an object with the 6 properties, 6 values basically. The value is the current value, so whatever it is, so it can be a number, a string. For a method, the value will be a method, a function. Writable determines or states if can be changed, if a new value can be assigned. Through get and set you can specify getter and setter functions. Configurable is whether the property or method can be deleted through delete object.syntax, and enumerable determines if the property shows up when you do a for in loop over the properties, for example, or you do object keys call. So in the case of simple method decorator, so in this case we're not using any factory, we're just using a simple decorator, so there's no execution function brackets afterwards. So in this case we're decorating this method. This method normally just returns 1, but here from the decorator we are returning a new property descriptor with the value key, and this with the new value is a new function which simply logs out that this replaced method is executed, and it returns 88. And when we run this code, even though we run foo, which normally would return 1 and not log anything, because we have decorated this method, we both get the console log and a new return value from that method. So yeah, that was a quite primitive, simple and useless example, but a more sensical, more useful would be, for example, to measure execution time for a method. So if you would create a decorator that keeps the original method but replaces it with a new function that takes in some amount of arguments and later applies it, keeping the target, the this context for that method to the very same target, very same class with the same arguments. So the method is applied originally it was intended to. However, that call is now wrapped into performance start and end calls, so you can measure how long it took for that method to run. You can, for example, log out the execution time difference in milliseconds, and at the end, of course, return original result that it was supposed to do. And then you would get something like this. So, for example, in this case, the foo stays the same it was. It returns 1, but we get a console log how long it took to run. There is a library, for example, helpful decorators for TypeScript. It has a lot of useful things. It might come handy sometime, like the bounce, throttle, once, and measure. I already showed, for example. So the bounce in the, for example, leans on loaders the bounce that makes sure a function is not run too many times within some time threshold. Same way you can decorate accessors. So let's say we have a class where we instantiate with the underscore name property, and we have a getter for that property, returns name. But when we do in for loop, it only logs out this this private property, because of course it logs a private property, because in JavaScript there are no private properties, at least in this when using this syntax. However, if you would, for example, use a decorator that updates the descriptor and sets the enumerable property to true for this accessor, logging out the same for in loop, you would since you updated the property descriptor, you would also have it enumerated and logged out when looping it over. With properties, you can, for example, devise a decorator where you set up a threshold for its maximum value. So from the decorator you would return a new property descriptor with getter and setter. So the getter would simply return the original value, whatever it is. However, the setter would first of all log that we're trying to set the value, but it would impose a ceiling on the value, so we just pick out the minimum from the max and the value being set. So if it's over the threshold, we will not go above that. So for example, if we would apply it to the property speed, so it wouldn't be able to set more than 10. I think I'm missing some lines here, but basically imagine that we are setting it to something higher, but it would still keep the maximum value to what we define in decorator. So that's one way to apply it. Parameter decorators let you get access to the class you're decorating, the name of the parameter in the method. So example here in this move method. But constructor property decorators don't have a name in this case, and you only get the index position of the property being decorated. In the current TypeScript specification, there is not much useful things you can do with it. Therefore, from the official documentation, it's intended to be used together, for example, with reflect metadata library that it gets you gives you access to more information about the object, and gets it to examine its own metadata, and then in combination with, for example, validate decorator, which you would apply both on a method and required on the property. Then you, for example, you could achieve that when you run this method, that this property, for example, is always present, that you cannot run it during runtime without it. But that's a bit more contrived and complicated example, and I don't want to go into that because the current TypeScript decorators are actually considered a legacy, and there's already a new standard in T39 proposal in stage 2. However, since it's not complete, it's still advised to use this legacy syntax, and TypeScript is staying with that. However, in the newly proposed standard, these parameter decorators are gone. So, well, we'll have class decorators, field decorators, there's property decorators, method and accessor decorators. So those 4 basic ones we looked into. But it will also have class prop field decorators and class initialized method decorators. But that's still in proposal state, so we will not go over it, because yeah, this is a TypeScript workshop. And that concludes this workshop presentation. I hope it was insightful. I understand that it might be too much to intake in one go, so if you did watch it in one sitting and you feel confused, I suggest you to take some time to sort of let it sink in and rewatch parts after a while again, or go read a bit of TypeScript documentation handbook. It's pretty insightful. A lot of in these slides was based upon the documentation, and I hope the time you spent watching this was worthwhile and will contribute to a better code that you write in your daily life. Thank you for watching this, and I hope to see you again in some other future presentation / workshop / anything. Thank you.